Section 1.5 linear equations in integrating factor. We're going to solve another type of equation. An equation that it's actually at first glance not separable. However, the point of this section is to come up with the magic touch to turn a not separable equation into a separable equation. All right? Well, so we're going to also talk about the error function, which is one of those special functions in engineering and applied mathematics. And I'm going to go back to applications to mixing problems, all right? Okay, so number one, the prerequisite we need to get through linear first order equations, it's the product rule, which you guys know it, right? I mean, take the derivative of that product, the derivative of x squared, which is 2x, times the second factor plus the derivative of the second factor. But be careful when we differentiate a y, this should be y prime x squared, because we're using the chain rule, right? This y depends on x. All right? That's what you know how to do, right? If I gave you, say, x squared e to the 5x, you can find the derivative of that product without even using a formula sheet at this point. However, this time, for this integrating factor, this magic touch we need to think of this in a backwards way. Then that's our first example here. Okay, so look at this. E to the 2xy prime plus 2 e to the 2xy. Does that look like the result of the derivative of a product? And if so, what is that function? d dx? What product of functions has the derivative equal to this madness here? Any ideas here? What was that? E to the 2x times y, right? So, what about the second, let's say letter B? Does that also look like the derivative of a product? So the derivative of y, which is dy dx, and then the derivative of arctangent, which is 1. There's an invisible 1 here, if you will, 1 over 1 plus x squared. So this means we are differentiating, with respect to x, the function arctangent of x times y. Notice the parentheses around the x because the y is not part of the argument here. All right? Okay, so let's identify, now that we have the prerequisite, well, we're going to use this later to get the solution to the equation. So number one, a differential equation of the form a sub 1 of x dy dx plus a 0 or a naught of x y equals some function of x. That's a linear first order equation. How come? Remember when we identified or classified equations by their linearity? So in this case, neither the y's or their derivatives are raised to powers other than 1, nor are functions of y like exponentials or trigonometrics, etc. So also the coefficients of y's are only depending on x, or could be just pure constants. That's fine. All right? Well, whenever we're given an equation like this, the first step we need to do is to divide both sides by a sub 1 of x. All right? To leave it in the form dy dx so that its coefficient equals to 1. And of course, we're going to get a quotient function right here, a naught over a1. That's just going to be another function, whatever that is. Let's just call it big P of x. And the quantity on the right-hand side, the g of x over a sub 1 of x, that's just some other function that we're just going to call f of x. All right? So, well, how are we going to solve this equation? Well, so the method relies on writing the left-hand side of the equation but in terms of the product of the derivative of some product, all right? Well, the formula, which is very simple, it's at the bottom of the page. However, I'm going to show you where is this formula come from, all right? So, So this is what we're going to do. So we're going to come up with a new function that we're going to call mu. That's the lowercase mu from Greek alphabet, and that's going to be our what we call the integrating factor, which again, that's the magic touch to turn a non-separable equation into a separable one. All right? Well, so consider this product. The derivative of this product is mu y prime plus mu prime y, all right? That's just using the product rule. And by the way, for the rest of the derivation, I'm going to omit the parenthesis x. In this case, it's safe to assume that everything is a function of x, all right? So, and that's just to be more compact with the derivation, all right? Okay, so we're going to multiply both sides of the linear equation, the one I showed you at the bottom of the previous page, by this mu, by this new function mu. Okay, that's going to give us what? Oh, by the way, I would like to call this, label this as 1. Okay, so that's going to be equal to mu y prime plus what is that going to be? Mu p y equals to mu f. Okay? I would like to call this number 2. Okay? I'd like to call this number 2. Now, because again, we want to make sure that the left-hand side of the equation, of the differential equation, looks like a product, so we can then turn that into a separable equation. What we're going to do, we're going to set the right-hand side of 1, that is the quantity in blue, equal to the left-hand side of 2. Okay? So that'll be, that'll be mu y prime plus mu y prime plus mu p y equals to mu y prime plus mu prime y, all right? So that's going to be a new equation. So here is the thing. In order for these for these to be a true statement, well, do you guys agree that here we have mu y prime equals to mu y prime? Okay, we can cancel it out if you want. However, I'm going to leave it like this. However, instead, what I would like to do, in order for this to keep being an equation, the coefficient of y right here, I think I had this backwards, has to be, okay, highlighter, mu prime, okay, equals to mu p, all right? Because the coefficient of y equals the coefficient of y. I'm going to set that on the side. I'm going to do some scratch work, okay? So, on the side, I'm going to do, so mu prime equals to mu p, okay? But I'm going to rewrite this mu prime as d mu over dx equals mu p. Isn't that a very simple, different, separable equation? We can separate the variables here by multiplying both sides by dx and dividing both sides by mu and integrate both sides. All right? Well, what's the integral of d mu over mu? ln, all right? That's ln of mu, all right? And what is this integral of p dx? Whatever that is, because right now we don't know what p is, all right? Okay? Well, let's solve for mu by exponentiating both sides. So that means mu equals to e to the integral of p dx, okay? And that's mu. That's the function. That's what we call the integrating factor. All right? So this is what we're going to do. I'm going to use this result I just got over here, this preliminary result. And I'm going to multiply. I'm going to go back to equation 2 and multiply both sides. So actually, what I have over here, so that is, okay, let me go back to, yes, blue. So that is mu, which is e to the integral of p dx, and that's times y prime, plus mu, well, not mu anymore. In this case, it's e to the integral of p dx times py equals to e to the integral of p dx times the function f. All right? Okay. Have a look at the left-hand side of the equation. Does that look like the product? I mean, does that look like the derivative of some product? It should. Okay, let me show you how. Okay, what's the derivative of y? Isn't that y prime right here? And what's the derivative of e to the integral of p? Isn't that this quantity, right? I mean, the derivative of this, isn't that quantity? If you're not sure about it, let me show you how I differentiate this exponential to the weird integral. So let me take the derivative with respect x of e to the integral of p dx. Okay. Number one, what's the derivative of the exponential? Isn't that itself? Okay. E to the integral of p dx times the derivative with respect x of the integral of p dx. But what's the derivative of the integral? Aren't they opposite operations? Then that's gonna leave me with simply e to the integral of p dx times p, which is that quantity. So that's definitely a product, right? That madness on the left-hand side of this equation. So now coming back to this equation, so this is the same as saying the derivative with respect x of, what is that? E to the integral of p dy, not dy, dx. Dx times p, well not p, that's y, equal to e to the integral p dx times f. But I don't like this huge formula. I'm going to write this result. We're almost done, by the way. I'm going to rewrite this form in a more compact way. But first of all, how about we can separate the variables? So now, that linear first order equation, which initially it wasn't separable, now it's separable. So I'm going to multiply both sides by dx. That's going to leave us with e to the integral of p dx times y equals to e to the integral of p dx. What else? And well, that's d. We were left with a d here. P dx f dx. Well, let's get rid of that d on the left-hand side. Integrate. The integral cancels the differential, the d. So that leaves us with e to the integral of p dx. Y equals to the integral of e to the integral of p dx f dx. And that's the final result we want. I'm going to rewrite this formula in a more compact way. Remember what was e to the integral of p dx? That's just mu, isn't it? So this is equal to mu y equals the integral of mu f dx, which is the formula we have down here. All right? So, and well, now let's get to solve some linear first order equations. Okay? So, well, the steps to solve an equation like this, make sure to write it in a way that the derivative term has only a 1 as a coefficient. All right? Number two, from there, identify your function p of x and your function f of x. The function p of x is whatever multiplies the y to the first power, and f of x whatever it's by itself on the right-hand side. So find the integrating factor and then simply substitute in this formula. All right? So if you watch the videos from the homework, you know how many of the homework questions have embedded videos. They may take a different approach. What they're going to do is multiply both sides of the equation by the integrating factor and then generate the product. Here, I'm just giving you the formula straight to the final result. All you do is substitute. And yes, I mean, this is very formulaic, but at least I'm showing you where is this baby formula coming from, all right? So let's go for it. Let's go and solve some of these linear first order equations. All right, well, solve each equation. I mean, xy prime plus 4y equals to x to the fifth power. Number one is the equation written in the form we want. That is the derivative term having a coefficient of 1? Not in this case, all right? So that means we need to do maybe a couple steps, divide both sides by x to get the equation y prime plus, I'm going to go 4 over x, y equals to x to the fourth. Okay? So from here, we can identify our p of x and our f of x. P of x is whatever is multiplied the y to the first power, which in this case, well, let me write it down for you. So p of x equals, what is that? 4 over x. And what about f of x? That's x to the 4, right? Okay. Well, all we have to do is obtain the integrating factor. That is, mu of x equals e to the integral of p dx, which is e to the integral of 4 over x dx. All right? Well, the integral of 4 over x, is that e to the 4 ln? Right? Well, can we simplify this a bit further? What can we do? Can I cancel the exponential with the ln? Just like this? Like, can I do this? Yes? Can I do that? Not yet, because we need to make sure the ln has a coefficient of 1 in front. So we need to use the smackdown basketball rule for logarithms. Yeah, let me show you how does that work. A to the ln of x equals ln of x to the a. If we go in this direction, what are we doing? Basketball with the coefficient? Basketball. Otherwise, the other way around, the a smacks down, right? So smackdown basketball rule, right? Yep, that makes it catchy to remember, all right? Well, so let's basketball this one first, all right? And mu equals e to the ln of x to the fourth. Cancel e with ln, mu equals x to the fourth. All right? Yes.
Do we ignore the plus c?
No, but good question. No plus c while we are getting the the integrating factor, because this is only an intermediate step. So the plus c will be generated at the very end when we use the formula, which is coming up next. All right. So what are we going to do? Mu y equals integral of mu y. Oh no, wait. Mu f dx, and we have everything we need, right? We just got mu, which happens to be x to the fourth, times y equals to the integral of, again, x to the fourth. But what is f? Isn't that another copy of x to the fourth? Okay. And well, let's simplify this. That's x to the fourth. Y equals to the integral of x to the 8th power dx. Now evaluate the integral on the right hand side. X to the fourth y, which is x to the 9th over 9 plus c. Here is where we come up with the plus c. All right. And well, I mean, all we can do right here is maybe multiply both sides by x to the negative 4, or divide both sides by x to the positive 4. Well, I'm going to do the division instead. Divide both sides by x to the fourth. And that's going to leave us with, let me continue here, y equals to x to the 9 divided by x to the 4. Isn't that x to the 5th over 9 plus c over x to the 4th. Final answer. Right? Final answer. And to briefly recap again, make sure, number one, make sure the equation is written in a way that the derivative term has a 1 as a coefficient. In this case, we needed to divide both sides by x or by any numerical x we have, all right? So identify P and F, which we had over here, and then we find the integrating factor by evaluating e to the integral of the function P, okay? Then, now that we got that mu, which is our integrating factor, just substitute it in the formula. The rest of the problem is next step, next step, next step. All right? So let's have a look at another example. Well, one example with an initial value problem, by the way. Now, well, let's have a look at this equation before solving it. Is it separable? So that is dy dx equals, I'm going to move the y to the right hand side, like x minus y. Do you guys agree that this equation is not separable? And the reason to that is because the right hand side cannot be written as a product of a function of simply x times a function of simply y. Now we have an addition, well, subtraction, right? But it's not separable. So that's why we need to use the integrating factor thing and all that. All right? Okay, well, in this case, the equation, it's already given in terms of in the formula 1. That is with the derivative term with a coefficient 1, so we can go ahead and identify our p of x, which equals 1, and our function f, which equals to x. Let me do f of x, right? Which is x. Okay. All right, mu, which is, okay, I'm just going to go mu, equals e to the integral of p dx, that equals e to the integral of 1 dx. Well, the integral of 1 is just 1, isn't it? It's just 1 times x, I mean. So that's e to the x, all right? And we're ready to go. We're ready to go back to the equation. So the solution to this equation, which is given by mu y equals to the integral of mu f dx, okay? Let's just substitute, right? Just substitute. And then work on the right-hand side only. So e to the x, y equals to, what is that? The integral of e to the x times, times x dx. All right. The question here is, any ideas how to evaluate the integral on the right-hand side? IBP. What is that? IBP. Integration by parts, right? IBP, integration by parts. Well, what do we have? Actually, you know what? I'm going to rewrite this integral so that it looks more familiar, right? Like what you used to see in a Calc 2 class, right? With the algebraic part in front of the exponential part. And well, you might remember the LIATE, right? LIATE, the acronym. And that's to identify our choice of u and then our dv, all right? How does that LIATE work? Well, you guys may have seen it in Calc 2 or may not, I don't know. Well, L stands for logarithm. Do we have a logarithmic function in our integrand? No. I stands for inverse trigonometric function. Do we have an arcsine, arctan? No. A stands for algebraic. Do we have an algebraic function like a polynomial, a radical? Yes. That x is it's going to be our u. Okay, so I'm gonna use the side right here. I'm gonna take a side trip here to say u equals to x. The rest of the integral will be e to the x dx, that's going to be our dv, equals e to the x dx. All right? So, well, what do we do with the u? Differentiate to get the du, which is dx. What do we do with the dv? The other way around. Integrate, and the integral of e to the x is just itself, e to the x, and just e to the x, right? Well, integration by parts. U times v minus the integral of v du, okay? And we have everything we need to set up our integration by parts. So u times v, which is x e to the x, minus the integral of v, which is e to the x, times du, which is du. All right? Another integral of e to the x. So this is going to be simply x e to the x minus e to the x. All right? And again, we're not going to put the c at this point. The c, we get the c when we get our final result. Okay, so now let's go back to the differential equation. All right? So this will be e to the x, y equals the integral, or no more integral, right? That's just x e to the x minus e to the x. Oh, here we put the plus c, right? Here is where we put the plus c. The processing green, that's just a side work to go with the integration by parts. And now when we're with the differential equation, here we put the c. Okay? How about divide both sides by e to the x, okay? So that'll give us y equals to x minus 1 plus c e to the negative x. Or c over e to the x. But usually the exponential functions, we write them with negative exponents. Either way, it's acceptable. All right? Well, so this is only our general solution. Okay? Now we need to look for the particular solution having initial condition at y of 0 equals to 4. Okay? So, with y of 0 equals to 4, which is x equals to 0 and y equals to 4. Okay, substitute the y into the with a 4, so 4 equals to y, and then 0 minus 1 plus c e to the negative 0. Okay, well, so there's going to be a lot of cancellations, very simple cancellations. Well, 0 minus 1, isn't that just negative 1? And then e to the negative 0, it's the same as e to the 0, which is also 1. And then 1 times c, isn't that just plus c? And then to solve for c, just add 1 to both sides. So c equals to 5. So we should go to the particular solution. Y equals to x minus 1 plus 5 e to the negative x. Right? General solution, particular solution. Okay? So, okay, let's see. Looks like that's about, the examples, all right? So, what's next? Okay, depending on the area of engineering or applied math. By the way, how many of you are math majors here? 1, 2, 3. Okay, quite a few. So, great, because I'm going to be doing a bunch of derivations and proofs, all right, throughout the semester. Not everything, because unfortunately we don't have time to prove everything, okay? However, those of you who are going to go as math majors, and many of the engineering majors are going to work with what we call the error function. And this is a function that comes when you're dealing with signals, filters, when you take Laplace and Fourier transforms to go from the world of analog to the world of digital. So that's essentially what you're going to do. Well, and oftentimes we're going to get a function like this. But what's the root of all this evil here? For instance, some integrals we can't evaluate them, right? When that happens, these functions are non-elementary. For instance, the integral of e to the x cubed dx. Unfortunately, we can't integrate this function because we're missing at least a factor of x squared to set up the u problem, right? Also, a function like, or an integral like sine of x squared dx. Same situation. We wish we had an x multiplying outside, right? But we don't have it. And we can't divide by x. We can only do that with constants, right? Well, so there is this function, the integral of e to the negative x squared dx, which is this special function called the error function. Well, the error function is defined as 2 over pi integral from 0 to x of e to the negative t squared. And we also have its complementary function where we go from 0 to x, and then the complement goes from x to infinity. All right? And well, we use this function is useful in upper levels of probability theory, statistics, and partial differential equations, and like I mentioned, in many other engineering applications, as you will see later. All right? I mean, in your future courses, not in this course. Also, what we're going to look at later in the semester is how the integral from 0 to infinity of e to the negative t squared equals to the square root of 2 over 2, which is related to the Laplace transform and many other fun things. The way we're going to get from this to there is by using just to give you the heads up, by using a double integral in polar coordinates. And well, yeah, it's kind of it's going to be probably the funkiest lecture you will ever have, right? It's because it relates to things that look totally unrelated, and then this is also related with the factorials, and then it relates to the Laplace transform, and that's just crazy. All right? Well, these two functions are related by the fact that error function of x plus complementary error function RC of x, they add up to 1. All right? So no wonder this is related to probability, because what is the range of a probability function? It goes from 0 to 1, right? Like 0 if an event is unlikely to happen or impossible to happen, and 1 if it's certain, right? So there's no way to say, it's 150% for this. No, it's between 0 and 100%, or 0 to 1, depending on how you go. Okay, so the purpose of the next exercise is to solve a linear first order equation and write the solution in terms of the error function, right? So, well, again, dy dx minus 2xy equals to 2 with initial condition 0 equal to 1. Okay? So we want to express the solution in terms of the error function again. Number 1, what's p of x? P of x equals to negative 2x. And what about f of x? Isn't that 2, right? Just 2. Well, actually, I'm going to use the space above instead because I may not have enough space below. So, mu will be e to the integral of p dx, which is e to the integral of negative 2x. Wait. The integral of negative 2x dx, which is e to the negative x squared, all right? So I think you can already see where we're heading to. This x squared, d squared, all that. Okay, so let's go and solve the equation that mu y equals the integral of mu f dx. The rest is just formulating, right? Substitute, etc. So, e to the negative x squared, y equal to the integral of e to the negative x squared, f, which is times 2, dx. And again, what happens here? We can't integrate this one right here, right? Unfortunately, we can't integrate, okay? Now, here is the tricky part. Suppose we were able to integrate, all right? So what if we can find some interval from 0 to x, all right? So if we integrate e to the negative x squared y, instead, if I put limits from 0 to x, of 2 e to the negative x squared dx, I could simply add the plus c right here. That looks weird, right? But why can I do that? Because what if we take the derivative on both sides? Do you guys agree that for some value of x, this would be a constant, right? And the derivative of a constant, isn't that equal to 0? The derivative of c, it's also going to be equal to 0, all right? Or even if we use the second fundamental theorem of calculus on this guy right here. So the derivative will take this to the world of, oh, actually I would have to express this in terms of t, not in terms of x, all right? That's a whole new variable, all right? So that when we use that second fundamental theorem, the derivative of this goes back to this function of x. And what is the derivative of c? Isn't that just 0? Which is that plus 0 we had over here, which I'm just going to undo it, all right? Okay, so let me multiply both sides by the e to the negative x squared. That is y, oh, not e to the negative, it's positive, right? That'll be y, I'm going to take the 2 outside of the integral, e to the x squared, integral of from 0 to x, e to the negative t squared dt, by the way, not dx, dt, plus c e to the x squared, right? Actually, does that look familiar from day one? It was the same problem that we used to verify that this was a solution to the differential equation using the second fundamental along with a product rule. All right? Well, this is only the general solution. Let's get the particular solution. This is what it gets a little weird. All right, well, I'm going to go on the side. All right, I'm going to go on the side and evaluate. So with y of 0 equals to 1, that equals, okay, y equals to 1 equals 2 times e to the x squared, which is 0 squared, integral from 0 to, oh, also the integral from 0 to 0. What's the integral from 0 to 0 of any function? 0. All right, so e to the negative t squared dt, okay, plus c e to the 0 squared. This means this whole madness right here equals to 0 because of the integral from 0 to 0. Everything cancels out. So that's going to leave us with, okay, what is that? E to the 0 squared, which is e to the 0, which equals to 1. All right? So that means 1 equals to, 1 equals to c, right? C equals to 1. Well, do I really need to write that 1? Not really. So y equals to 2 e to the x squared, integral from 0 to x, e to the negative t squared dt, plus 1 times e to the x squared. Okay?
Did we just write error?
That's the next step. Oh. Let me write down the definition of the error function here. So the error function equals 2 over the square root of pi, integral from 0 to x, e to the t squared, negative t squared dt. So I'm going to solve, in this case, for, I'm going to move the pi. So 2 times integral from 0 to x of e to the negative t squared dt equals square root of pi f of x. All right? And I'm going to replace this right here along with the 2. Okay? So this will be, finally, in terms of the error function, y equals, actually, how about we factor out the e to the x squared? That equals 2 times the integral from 0 to x, e to the negative t squared dt, plus 1. And this guy equal to that guy goes over here. This is equal to y equals e to the x squared square root of pi error function of x plus 1. So all we're doing here is just introducing a new kind of function. Again, that's a function you may get to work in electrical circuits, in applied higher levels of applied mathematics or statistics and probability. So you'll see it more often than not. We may get to see it when we get to the Laplace transform, by the way. So at least I'm giving you a glimpse of it. Okay? Okay, yes. Hopefully that's enough time to solve the next problem. Okay, so the next. Oh wait, no. Again, I'm thinking of 6:10 again. It's 6:35. Yeah. All right. So I would like it's only 20 minutes. No. It's 6:35. Okay. So what do we have for this application problem? So remember that problem we did about mixtures last time, no, it was last time. Yeah. At the end of separable equations. Well, in that situation, we had a tank where some solution, well, it was brine in this case, some brine solution was coming into the tank and was leaving the tank exactly at the same velocity or rate at which it was coming into. However, there's other situations in which it may come into the tank at a faster velocity than it comes out. So that means eventually the tank will overflow, right? It will fill in. Okay, so let's have a look at this one. Okay, so a large tank contains 300 gallons of brine solution with 40 pounds of dissolved salt. All right. A solution with a concentration of 2 pounds per gallon is pumped in at a rate of 4 gallons per minute. The solution in the tank is very well seared and flows out outside of the tank at a rate of 3 gallons per minute. The question here is how much salt is in the tank after 12 minutes. Well, number one, I would like to draw a picture about it. I mean, it always helps. So, what do we have? So we have brine coming into at a rate of 4 gallons per minute. And it's leaving at a rate of 3 gallons per minute. So that means, regardless of how much we have inside of the tank, okay, it says we already have 300 gallons, right? So that means for every minute, we're going to gain 1 more gallon, right? That is the difference between what comes in minus what it comes out, right? So this is key, all right? This is one of the subtleties of the problem that if we don't take into consideration, the problem becomes very tricky, but it's important to stress on this, okay? So, also we know the concentration of the brine coming in, that is 2 pounds per gallon of NaCl, right? Of salt. All right? Okay. Now think about the situation. So we already have 300 gallons with 40 pounds dissolved. Well, we're getting more brine coming in with a given concentration. So whatever comes out will have a variable concentration. The concentration is not going to be exactly the same, right? So that's something else to keep in mind. Now, so we want to investigate the net rate of change between the amount of salt with respect time. And to do this, we will do based on rate in minus rate out. Because we're subtracting, we're looking at derivatives. Derivative of what comes in minus derivative of what comes out. All right? So, how do we explain this to? Okay, the ADT. This is equal to, again, flow in rate times the concentration in minus flow out rate times the concentration out. Okay. So the problem we did in a couple sections ago had a concentration in equal to 0 because we only had water coming in, right? We didn't have any salt coming in. We were actually on a process of dissolving water already on a container, and it was also coming into a rate coming into a given rate and getting out of the tank exactly at the same rate. So naturally, this was going to be a dissolving process, right? So lowering the concentration. Also, the fact that we have different rates, different flowing rates, that's going to make the equations likely different. All right, so dAdt. dAdt, that is flow in rate. That is the speed or the rate at which the solution is coming in. Isn't that 4 gallons per minute? All right. And the concentration in, which is 2, minus the flow out rate, okay? The flow out rate, which is, what was that, 3? Okay, that is 3 times, here is going to be a little tricky, the concentration out. How do we measure the concentration in this solution? The concentration is only the ratio between the amount of salt divided by the total volume, which is something similar you do in chemistry, right? And I'm not talking the molarity or the normality, no, I'm just talking about the ratio of amount of solute per unit of volume, right? It's a simpler way. Of course, I mean, we could have been given this problem in terms of chemical units, normal, molar again, you know, but that's not the case. Okay, so, well, in this case, the amount of salt, do you guys agree this is going to be variable? Whatever comes out, I'm just going to express it as A, all right? Because that varies with respect to time. Now, what about the volume? What about the volume? So initially, the volume is 300 gallons, right? 300 gallons. However, because every minute, T, by the way, the variable T is measured in, what is that, minute, right? So every minute, we will have one more gallon, right? So, plus 4 minus 3, T. Where am I getting this 4 minus 3 from? Well, again, that's the difference between what comes in minus what comes out, giving us a net increase of 1 more gallon, right? So, what's 4 minus 3? Just 1. So, dA dt equals to 8 minus 3A over 300, or I'm going to go T, 4 minus 3 equals 1 times C is just T plus 300. All right? If we had 5 gallons per minute coming in and 2 gallons per minute going out, 5 minus 2, is that equal to 3? This would have been a 3 here. All right? I mean, I'm just going the what if. So when you go back home and watch this video again to make more sense about this. All right? Okay. All right. Well, actually, this is a linear first order equation. We can't separate this equation because what do we have? The derivative term right here, okay? Some function of the independent variable, which in this case is not x, actually is t, times the dependent variable a, and then a constant function that can be left on the right-hand side of the equation. So what I'm going to do here is move this big term to the left-hand side. So dA dt equals, what is that? 3, we're not equal to, plus 3 over t plus 300 times a equals to 8. Does that look like a linear first order equation? Right? Mm-hmm. So what's in this case p? Isn't that 3 over t plus 300? And what's f? Isn't that just 8? Forget about the context of the situation. Let's focus on solving the differential equation. So at this stage, we're going to get the integrating factor mu equals to e to the integral of p dx, which equals e to the integral of 3 over t plus 300 dx. Yeah, it looks like a big term, but actually that doesn't seem like the hardest integral to evaluate in the exponent, because this 3 is just a multiple constant, and the integral of 1 over t plus 300, isn't that simply e to the 3 times ln of t plus 300? All right? And notice I'm putting parentheses as opposed to the usual absolute value bars. And that's because, well, in this case, we're not going to consider any negative times, right? So, yes.
Should they all be DTs?
You're right. You're right. Much better. dt. dt. Otherwise, that would look like a partial integral, right? So, well, I can't cancel out e with ln. In order to do that, I would need to basketball the coefficient of ln, right? So mu equals e to the ln of t plus 300 cubed, and this is equal to t plus 300 cubed. All right? Back to the differential equation. Well, actually, to the formula that solves the equation. That is, okay, it would have been mu y equals to the integral of p f dx. All right, that's the formula I showed you where it came from. However, let's adapt this formula to the variables we have in the context of the solution. So the function y this time, the dependent variable y this time, is the letter a. So that'll be mu a equals to the integral of p. It's still mu f, but instead of dx, it will be a dt. All right? It will be a dt. Formula A. Substitute. So mu, which is t plus 300 cubed, a equals to the integral of t plus 300 cubed, but what's f? 8, right? dx. Well, come on, dt. All right, dt, not dx, dt. Well, to evaluate this integral, do you want to cube the binomial? Not really. So t plus 300 cubed a equals to 8 times t plus 300 to the 4th power over 4. This is an immediate integral, right? Plus some constant of integration, of course. All right? And we're only one step, well, a couple steps away. Actually, I would like to reduce 8 divided by 4. Is that equal to 2? So that's t plus 300 cubed a equals to 2 times t plus 300 to the 4th power plus c. And let's divide both sides by quantity in parentheses cubed. And that should give us the result. All right? That is a equals to 4 over 3. Is that 2 times t plus 300 plus c divided by t plus 300 cubed. But guys, this is only the general solution. If we go back to the context of the situation, the context of the problem, they're actually asking us a question. They're asking us how much salt is in the tank after 12 minutes. I mean, I could substitute 12 t equals to 12, but what about that c? We need to substitute something to get the c, and we need an initial condition. However, we are not given something like y of 0 equals to 5 in the problem, right? So this means this initial condition, it's actually in disguise, right? Let's go back to the top of the problem right here. Okay. Okay, in this case, the dependent variable, which happens to be a, all right? What is that? Initially, A, which is the amount of salt, how much salt is initially in the tank? 40 pounds, right? I'm not asking for the concentration, but the A, amount of salt, amount of the solute only. All right? So this means with A of 0 equals to 40, because, and again, where is this coming from? Because initially in the tank, along with the 300 gallons of water, there are 40 grams of 40 pounds of salt. All right? Okay, substitute A equals to 40, all right? And that equals to 2 times 0 plus 300 plus C over 0 plus 300 quantity cubed. Okay. I forgot to substitute the 0. Oh, no, we're good, we're good. Okay, so 300 times 2, that's 400. That's 400 equals to 600. No, not 400, 40. That's 40 equals to 600. And plus C over 0 plus 300 quantity cubed. Don't cube the number. Just leave it as 300 cubed. Okay? Okay, let's solve for the variable C right here. 40 minus 600, is that equal to, okay, that leaves us with C over 300 cubed equal to negative 560. And then multiply both sides by 300 cubed. Negative 560 times 300 cubed. So it's quite a big number. So C will be equal to a big number. If you use your calculator, you may get a number in scientific notation. I'm going to give you the big number. That is negative 50 billion 120 million. Yeah, you're going to get negative 1.512 times 10 to the 10th power. All right, that's what you get. Okay. And of course, I mean, you can verify these numbers later with your calculator. All right, back to the equation, particular solution, finally A of t. Notice I skipped the parentheses t just to keep the simplicity of the notation. All right, so A of t will be 2 times t plus 300 plus c, which is, or rather minus, because it's a negative number, 50 billion 120 million over t plus 300 cubed. All right. Now we're ready to answer the question, finally. All right. So they're asking us the amount of salt after 12 minutes. After 12 minutes. So A of t, A of 12 equals to, what is that? 2 times 12 plus 300 minus 15 billion 120 million over 12 plus 300 cubed. All right? And just use your calculator to evaluate this. This is going to be approximately 126.12 pounds of salt. All right? All right. That's final answer. Finally. Okay.